When you unlock your phone with your face, Netflix suggests a show you end up binge-watching, or your email filters out spam before you even see it. Congratulations, you're experiencing machine learning in action. But what exactly is machine learning? How do computers actually learn without being explicitly programmed for every single scenario? Today, we're pulling back the curtain on machine learning. We'll explore what it really is, how it works, why it sometimes fails, and what you need to know to understand the technology shaping our world. By the end, you'll have a solid grasp of the fundamentals that power everything from voice assistants to medical diagnosis systems. Let's demystify machine learning. Traditional computer programming works like following a recipe. A programmer writes explicit instructions. If the user clicks this button, do that action. If the temperature is above 75 degrees, turn on the air conditioning. Every scenario is anticipated and coded. Machine learning rewrites the rules. We now feed computers examples and let them figure out the patterns themselves. It's less like following a recipe and more like learning to cook by tasting hundreds of dishes and understanding what makes them work. Think about how you learned to recognize cats. Nobody gave you an explicit formula. If it has pointed ears, whiskers, and fur, it's a cat. Instead, you saw many cats, many dogs, many other animals, and your brain learned to distinguish the patterns that make a cat a cat. Machine learning works similarly. We show computers thousands of examples, and they learn to recognize patterns in the data. There are three main types of machine learning, each suited to different problems. Supervised learning is like learning with a teacher. You provide the computer with labeled examples, images tagged as cat or dog, emails marked as spam or not spam, and it learns to map inputs to correct outputs. When you show it new, unlabeled data, it predicts the answer based on patterns it learned. This is the most common type of machine learning and powers applications like image recognition, language translation, and price prediction. Unsupervised learning is like exploring without a guide. Here, you give the computer unlabeled data and ask it to find hidden patterns or structure. For example, a streaming service might use unsupervised learning to group users with similar viewing habits without being told what those groups should be. It discovers clusters, maybe documentary enthusiasts or comedy binge watchers, purely from the data. It's about finding structure in chaos. Reinforcement learning is like training a dog with treats. The computer learns by trial and error, receiving rewards for good actions and penalties for bad ones. This is how computers learn to play chess at superhuman levels, by playing millions of games against themselves, discovering which moves lead to victory. Self-driving cars use reinforcement learning to navigate roads, learning from countless simulated scenarios before hitting real streets. Each type has its place, and often, real-world systems combine multiple approaches. But regardless of the type, they all share a common foundation: learning from data. If machine learning is like cooking, data is your ingredients. And just like cooking, the quality of what you put in determines what you get out. Let's walk through the journey data takes to train a machine learning model. First, we need features. These are the measurable characteristics we feed into our model. If we're predicting house prices, for example, features might include square footage, number of bedrooms, location, and age of the home. Choosing the right features is part art, part science. Too few features and the model lacks information. Too many irrelevant features and you add noise that confuses learning. For supervised learning, each example also needs a label, the correct answer we want the model to predict. For house prices, that's the actual sale price. For spam detection, it's whether humans marked each email as spam or legitimate. Labels are your ground truth. Once we have our data, we split it into 3 sets. This is crucial and often misunderstood. The training set, typically 60 to 70% of your data, is what the model learns from. It's like practice problems in school. The validation set, maybe 15 to 20% of your data, is used during training to tune the model and make decisions about its structure. Think of it as practice tests that help you adjust your study strategy. The test set, the remaining 15 to 20%, is data the model has never seen. This is your final exam. It tells you how well your model will perform in the real world. If you use your test set during development, you're essentially peeking at the exam answers, and your performance estimates become unreliable. How do we measure success? Through metrics appropriate to the problem. For classification tasks like spam detection, we might use accuracy. For regression tasks like price prediction, we might measure the average error between predicted and actual values. But here's the critical part. No single metric tells the whole story, which we'll explore more when we discuss bias. The biggest dangers in this pipeline are overfitting and underfitting. Underfitting is like a student who memorizes, "The mitochondria is the powerhouse of the cell," but doesn't understand biology. The model is too simple. It hasn't learned enough from the training data to make accurate predictions, even on that same training data. It performs poorly everywhere. Overfitting is like a student who memorizes every practice problem word for word but can't solve new variations. The model learns the training data too well, including its noise and quirks, and fails to generalize to new situations. It aces the practice problems but bombs the real test. This is incredibly common. A model might achieve 99% accuracy on training data, but only 70% on new data because it essentially memorized rather than learned. The art is finding the sweet spot. A model complex enough to capture real patterns, but simple enough to generalize to new data. It's a constant balancing act. And here's where things get messy and where many real-world machine learning systems go wrong. Let's say we build a model to detect a rare disease that affects 1% of the population. We train it on a dataset of 10,000 people, where 100 have the disease and 9,900 don't. We proudly announce our model achieves 99% accuracy. Sounds incredible, right? But what if our model simply labels everyone as healthy? It would be wrong about all 100 sick people, but right about the 9,900 healthy ones. 99% accuracy with zero medical value. This is the accuracy trap. When classes are imbalanced, accuracy alone is meaningless. Better metrics might include precision. When we say someone is sick, how often are we right? How many actually sick people do we identify? For a disease detector, high recall is crucial. We'd rather flag healthy people for follow-up testing than miss sick ones. Context determines which metrics matter. Then there's bias in the data, and this is where machine learning can amplify societal problems rather than solve them. If we train a hiring algorithm on historical data from a company that predominantly hired men for technical roles, the model learns this pattern. It may systematically downrank qualified women not because of explicit programming, but because it learned from biased historical decisions. The algorithm doesn't know it's being discriminatory. It's simply replicating patterns in its training data. Or consider facial recognition systems trained predominantly on lighter-skinned faces. Studies have shown these systems perform significantly worse on darker-skinned individuals, particularly women. The bias isn't in the algorithm itself, but in the skewed training data that doesn't represent the diversity of real-world faces. The hardest part is that machine learning models don't know what they don't know. They'll make predictions with equal confidence in familiar and unfamiliar situations. This is why machine learning isn't just a technical problem. It requires understanding the domain, questioning the data, auditing for bias, and constantly monitoring performance in the real world. The fanciest algorithm can't compensate for fundamentally flawed data. Now let's bring this to life with 3 concrete examples that touch your daily life. Case study. 1. Spam filtering. We talked about spam filtering earlier in the video. Your email provider processes billions of messages daily, and you rarely see spam. How? Through supervised learning. Engineers collect massive datasets of emails, labeled by users as spam or legitimate. But spammers adapt. They constantly evolve tactics. So spam filters must continuously retrain on fresh examples, learning new patterns. The model also uses signals beyond the message itself, like sender reputation and whether similar emails were marked as spam by others. The challenge? False positives. Marking a legitimate email as spam can mean a missed job offer or important medical results. So the system acts on the side of caution with uncertain cases, using confidence scores rather than binary decisions. Case study 2. Recommendation systems. When Netflix suggests what to watch next, it's using collaborative filtering, a form of unsupervised learning that finds patterns in viewing behavior. If you and another user both loved the same 10 shows, and they also loved an 11th show you haven't seen, there's a good chance you'll like that 11th show too. But recommendations aren't just about matching tastes. They consider what keeps people engaged, what's trending, what content Netflix wants to promote, viewing time of day, device type, and dozens of other signals. Multiple models work together. One predicts what you'll like. Another predicts what you'll actually click. Another predicts whether you'll finish watching. The trap? Filter bubbles. If recommendations only show you content similar to what you've watched, you never discover new genres or perspectives. Too much exploitation creates boring, narrow recommendations. Too much exploration frustrates users with irrelevant suggestions. Case Study 3. Credit Risk Scoring. Banks use machine learning to decide who gets loans and at what interest rate. They train models on historical data, previous borrowers' financial information, employment history, and whether they repaid loans. The model learns patterns that correlate with repayment reliability. Here's where ethics gets complicated. What if zip codes are a strong predictor of loan repayment? The model might use it to make more accurate predictions overall, but zip codes correlate with race due to historical housing discrimination. Using it could perpetuate inequity even if race itself isn't an input feature. This is called proxy discrimination. Some jurisdictions now mandate fairness audits, checking that models don't discriminate across protected groups. But fair has multiple mathematical definitions that can conflict with each other. Equal approval rates across groups, equal accuracy across groups, equal outcomes for equally qualified individuals. You often can't optimize for all simultaneously. These are fundamentally valued judgments, not technical problems. So let's bring it all together with 3 essential takeaways. First, machine learning is pattern recognition, not magic. Models learn from examples and generalize to new situations by finding statistical patterns in data. They don't understand in any human sense. They map inputs to outputs based on what worked in their training data. This makes them powerful but brittle outside their training distribution. Second, data quality determines everything. The most sophisticated algorithm can't overcome biased, incomplete, or outdated training data. Garbage in, garbage out. And accuracy alone is a misleading metric. You must understand the context, the class distribution, the costs of different types of errors, and whether your data represents the real world. And lastly, machine learning inherits human biases and requires human judgment. These systems amplify patterns in our data, including our prejudices and blind spots. Deploying them responsibly requires constant vigilance, fairness audits, and willingness to prioritize equity over raw performance. Technology is never neutral. Machine learning is reshaping medicine, finance, transportation, entertainment, and nearly every other domain. Understanding its capabilities and limitations isn't optional anymore. It's essential citizenship in the 21st century. Until next time, stay curious, stay critical, and keep learning.